So in this video, we talk about the fundamental theorem of invertible matrices, probably one of the top 3 important theorems in the entire course. So the fundamental theorem of invertible matrices starts this way. So assume you have a square matrix A. The following things are equivalent. That means if one is true, all of these are true. If any is false, all of them are false. So A is invertible. A times X equals B has a unique solution for every B in Rn. AX equals 0 has only one solution, X equals 0. The reduced row echelon form of A is I, the identity matrix, and A is expressible as a product of elementary matrices. This theorem is incredibly powerful. It is something that's so strong that we want to connect everything we do back to it. So as we introduce more and more ideas, more concepts, we'll constantly add on to this theorem. So this is only part 1 of many. So this theorem is so important, it deserves a proof. I'm going to establish the validity of the theorem by going and creating a circular bit of logic. So we'll show that if A is true, then B is true. If B is true, then C is true, and vice versa. C will imply D, D will imply statement E, and E will go back and imply statement A again. So if one is true, they all imply each other. Thing is, though, that in this particular argument, that we've already actually done a couple of them. I've already shown you that A implies B, and I've already shown you that statement B implies statement C, or at least I've implied how it's done. So I won't do those. I'll focus on the others. So let's go ahead and show you that statement C implies statement D. So I wrote down the 2 statements for you. I'm just going to fill in the middle of the proof. So I'm going to assume that A times X equals 0 has only X equals 0 as a solution. I will show you that the row reduced echelon form of A has to be the identity matrix. It's not really hard to see why, based upon the work we did with Gaussian elimination. So if A times X equals 0 has only the 0 solution, it means it has to have the same solution set as I times X equals 0, because I times X equals 0 has only X equals 0 as a solution. Those systems, therefore, are equivalent systems. Well, we know already, though, if they're equivalent systems, that means that if you put A with 0, the augmented matrix, and write down I with 0, the augmented matrix, those matrices have got to be row equivalent. You have to be able to row reduce one to the other. That means then there has to be a sequence of row operations so that the row reduced echelon form of A is I. And that's that proof. Now for D to E. Let's assume that A can be row reduced to the identity matrix. I will show that because of that, it can be expressed as a product of elementary matrices. To do so, remember now that if A can be row reduced to the identity, there's just a sequence of row operations that do that. So there's some sequence of row operations, let's say there's K of them, that row reduce A to I. But we also know that for every single one of those row operations, there's a corresponding elementary matrix so that we can do that row operation instead by matrix multiplication on the left-hand side of the matrix, as I wrote down here. But that's now a matrix equation. With that matrix equation, we know that all the elementary matrices are invertible. Therefore, the product of them is invertible. And I can then go and solve for A by just taking the inverse of the product of those elementary matrices on each side. But then we know that the product, an inverse of a product, is a product of a bunch of inverses just in the reverse order. And so you can then get that A is therefore equal to a product of these inverse matrices times I. The times I doesn't do anything. But then we remember that the inverse of an elementary matrix is actually an elementary matrix. So I just showed you that A then is therefore expressible as a product of elementary matrices. Now that particular result is symbolic, and because of that, people have a hard time seeing it. It's something you've already seen. I've gone and shown you that if you take this matrix and you could row reduce it to that one, you can always reverse it. It's the same statement. It's just expressed in terms of matrix multiplication and elementary matrices. I'll show you what I mean. So start with the matrix 1, 0, 3, 2. Let's row reduce that to an identity. So we can do that with these two row operations in order. Now you can express those row operations as elementary matrices and just multiply the matrix 1, 0, 3, 2 on the left-hand side. On the right-hand side, you'll then get the identity matrix. That's that. I even wrote down the matrices for you, so you can see what these elementary matrices would have to be in this case. Notice that they are in opposite order because you apply 1 first on the left, and then to that on the left, you apply row operation 2, which is done by matrix multiplication by E2. But we also know, though, that these row operations can be reversed. So start with the identity and go and use 2 times the second row. That would then give you the matrix 1, 0, 0, 2, and then use the inverse row operation for the first row operation to get back to the original matrix. But symbolically, that means that all I did was to the identity, I applied certain row operations, which can be expressed as row operations, or in this case, matrix multiplication. They just happen to be the inverse row operations, and therefore the matrices are the corresponding elementary matrices for those inverse row operations. So that's what I did down here for you. I wrote down that the identity matrix, when I apply these row operations expressed as matrix multiplication, I get the original matrix. Notice, though, that these things are multiplied to I. So then the original matrix is this product of elementary row operations. So that's kind of neat that if you keep track of the row operations, when you take a matrix all the way down to the identity, if you think about it, notice the row operations are in the exact same order. So it's 1 and it's 2, 1 and it's 2, but you use the inverse row operations and those matrices here and here in that product, that will then give you the original matrix. So this is just something you've already seen before. It's just expressed now in terms of matrix multiplication. So the last one, assume that A is actually a product of elementary matrices. Well, each elementary matrix is invertible. So then I have a product of invertible matrices. I know from the theorem I already showed you that therefore, since I have a product of invertible matrices, the resulting result is invertible. So that's that proof. That's pretty neat. So now we now know that all these things are equivalent to each other. I think it's a good idea to show you at least like one cool way this can be used. And it's certainly one of the reasons we went through all this work today is to get to this surprising consequence. So how do we find the inverse? Like I've done all this work, but I've never actually said, here's the way to find the inverse. So now we can do that though. So suppose that A is an n by n matrix. We know that it's invertible if and only if it can be row reduced to the identity. So if it can be row reduced to an identity, it has an inverse. If it cannot be row reduced to an identity, then it cannot be, it does not have an inverse. So let's just suppose that it can be row reduced to an identity. But that means then that there has to be elementary matrices that do those row operations. Let's just say there's k of them that do so. So then if you apply those row operations as expressed as matrix multiplication on the left-hand side by elementary matrices, you get this algebraic statement. But remember though, that we know that if it can be row reduced to the identity, that means it has an inverse. So I can then take that A and multiply the equation you see on the right-hand side by A inverse. And that gives you that. Now that looks not that important, right? It's just an algebraic statement. But remember though, that elementary matrices, when applied on the left-hand side of a matrix, actually does that row operation. So then on the left-hand side, I'm applying the exact same row operations in the exact same order that I used on A to reduce it to I. I'm just now applying those row operations to I first. And when you do all those row operations, you get the identity. So you get the inverse matrix. So this then says that if you want, take an augmented matrix, but this time when you put the bar, don't put down just one column, put down the entire identity matrix on the right-hand side. Row reduce the left-hand side, matrix A, to the identity. If it cannot be row reduced to the identity, then A has no inverse. If it can be row reduced to the identity, then the right-hand side, when you apply those exact same row operations to I, you'll get the inverse. That's really fantastic. It means we can use Gaussian elimination to find the inverse matrix. I think you should see it. So then this matrix here, I claim it has the inverse. How do I know? Because if I go and write down that matrix and I adjoin it with the identity, and I row reduce the left-hand side to the identity, I now know that the matrix has an inverse because it can be row reduced to the identity. And also because of the theorem I just proved to you, and one of these really great consequences, using those exact same row operations on the identity matrix, converts it into the inverse. So that this thing right here, that's the inverse matrix of the original matrix. It's neat, right? It's great. So that's that the inverse of that matrix is just what I just had. That's fantastic. That's a great result. So there's other ones too. This one I won't prove though, it's the last one. Another great consequence just happens to be that if you ever have two matrices of the exact same size, that when you multiply them, you get the identity. That means both matrices are actually invertible and they're actually inverses of each other. It also means, by the way, that means that A times B has got to be B times A, because that's what it means to be an inverse, right? They automatically get that commutativity. So if you ever want to prove that two matrices are inverses, you only have to do the multiplication in one order. So while the definition insists you need both, you don't actually. You only need one side. So that means that if you go back to the original problem I gave way back when at the beginning, I claimed that the matrix 1, 2, 1, 3 had an inverse matrix, and it was 3, -2, -1, 1. I only have to do one of those matrix multiplications, actually in either order, to show you that I get the identity. Then because of this theorem, as a consequence of the following order equivalence theorem, we get they're actually inverses of each other instantly. And I think that's it. That's it for today.